All right, welcome back. And today we are going to do a little bit of trees. So we'll start off with some pretty easy questions, like this one. This one is called maximum depth binary tree. So usually with binary trees, I usually like to use recursion because it's usually how it's taught anyways, but let's go through it. And it's also a lot easier to implement when you use recursion. The only thing about recursion is that sometimes it might be slower because sometimes there's a better dynamic programming version of it. But usually for trees it's okay. And sometimes you might have like Stack Overflow, which isn't a good thing. So maybe sometimes you have to do it the iterative version. But let's look at this question. Maximum depth of a tree. Given a binary tree, find its maximum depth. The maximum depth is the number of nodes along the longest path from the root down to the furthest leaf node. Okay, cool. So for example, if we see this tree, 3, 9, 20, 15, 7, the depth should be 1, 2, 3, right? Because the last node here is 1, 2, 3, 3 down. So imagine if 15 did not exist, it would still be 3 because the depth is 3, 1, 2, 3. So meaning if there's just one, it's 1. Like if there's just one node, the depth is 1. Okay, cool. So let's go on to the iPad now. Let's draw a little bit. So we're gonna take the same example, 20, 15, and 7. Now usually in these questions, what you get is the class. The class structure looks like this, right? You have a tree node, and then this is what you're given. And then what a tree node has is it has a value, a left element, and then a right element, right? Usually a value could be an int or like a string. It's basically the value. And then the left would be another tree node. And then right would be another tree node. Yeah, we explain it more in Tech Interview Pro, but this is how a tree node is structured. And then for a tree, you're just given the tree node that is the root. So you're gonna start here, right? So the first way of doing it is by recursion. And how do you do this by recursion? It's actually very, very simple. You should know pretty well how to do recursion by now. Like we can look into it a little bit more. So imagine if we have this tree. Yeah, so then we have this node, right? And then what you want to do for recursion is you want to remember what's the base case. Always remember what's the base case, and then what is, I guess, the recursion case, and then recurse, right? Base case is when you don't need to recurse. You're at the end of your recursion. So at the end of recursion, what do you know? If you know that you have nothing, like if the tree is empty, like usually look at the edge cases here, and the edge case actually helps you write the recursion. So base case is if tree node is null, right? Imagine if I just give you an empty tree. This I'll call empty tree, and then like let's pretend 3, that's like one node tree. And then this is like a normal tree, 3, 9, 20, 7, 15, right? So here you got the empty tree, one node tree. Yeah. So then this would be a base case because you don't need to recurse anymore. So we have one case. The base case is if tree null is null. So if that's the case, I just want to return 0, right? And then one node, it would make sense if I returned 1. But you don't even need that because you can actually just re-recurse later on. And I'll show you why. So basically, how do you know? So if I was a node, and then I want to know what the maximum depth is. Imagine I am node number 3, right? And if I am node number 3, then I want to know what the max depth is of my left subtree and versus what my max depth of my right subtree. So for example, I am 3. I want to know on the left side, what's the deepest node? In that, the answer is 1. And then on my right side, the deepest is 2. So that means for me, I know that my tree, starting from the root, and I'm root 3, is the maximum of my left subtree and the maximum of my right subtree plus 1. So which one's bigger? 2 is bigger, and then I add 1 because I am myself a node, and that would be 3. So does that make any sense? What we want to do is we want to call recursively the same function, because this function that we're writing, we're actually reusing. That's the basis of recursion. So, okay, I think you guys understand. So yeah, so that's what we do. We just check the left one. We say, all right, on the left one, what's the maximum depth? On the right one, what's the maximum depth? And then we recurse. Okay, so let's write that on the actual program. So very simple, like I said, base case, right? The base case is this one. If root is none, then return 0. And then what you want to do is you want to return the number, which is the max of either the right or left subtree, the max of left and right subtree, their depth, plus 1. So I'm just going to return the max of, and I'm recalling my function, right, max of that, plus 1, which is myself. And then would that work? Like, you'll have to test in your brain. You're like, oh, would that work with only one element? It would, because you're going to be returning max depth would be 0, max depth left would be 0, plus 1. So if you run this code, it works perfectly fine. Okay, excellent. So it works. So what is the time complexity of this algorithm? Well, when you think about it, when you do the max depth on the right and the max depth on the left, you are going through all the nodes just once, because you're not going to revisit the nodes, because once you call max depth on the right, it will only call it once to the right and the left, and every node will be just visited once. So how many nodes there are? There are n nodes, so that means the time complexity for this is O of n. Yeah, and then in terms of space complexity, what is it? The space complexity, here it seems like, oh, I'm not really using any variables, or I'm not making any new data structures, so it's O of 1, right? No, it's not, because you have the call stack, and then the call stack is actually like using memory. So it depends how far your call stack goes. Like, how deep do we go? Like, okay, actually, let's draw this out a little bit. So when you think about it, every time I call recursion, for example, max depth, the first one I will call, and then what happens is I'll call another version of max depth, which that's why they call it a call stack, because you keep calling the same function or different functions, and then you keep calling another one, and then usually once you hit null, then that's when you stop calling. That's when you start popping, and then maybe you start calling the left one, for example, max depth left. Okay, so actually let me kind of illustrate a little bit more. 3, 1, 2, 5. This is not a binary search tree, by the way. This is just a binary tree. Okay, so we start at 3, so the call stack is like this. I am currently calling 3. Okay, I'll just name the value, but imagine this is a function call. And then we're gonna call left, and then the left one is gonna be 1, and then we're here 1, we're gonna call the left one, and then this is another null, and then after the left one, we're gonna call, we're gonna go back to this stack, because we realize there's nothing there. And then we'll call here, which is another null, right? And then you pop the stack again. So you pop this, so you're done with this one now. And then you're gonna start calling the right one. And then now that you call the right one, we start here, which is a 2. And then for 2, it's gonna call the left one first. It's gonna go 5. And then once it's 5, it's gonna call null, right? And then we're gonna call the right one, which is also null. And then now 5 is done, so it's gonna call back to the second one. Oops, I can just erase this. So then this is gone, and then 2 is going to call 6, and then it's gonna call 6, and then same thing, null, and then null 2 times, right? Because 2 times null. And then 6 is gonna be erased because 6 is done. It has finished executing. And then 2, because we've done left and right already, it's gonna also be done executing. And then now finally 3, we've finished executing its right subtree, which is complete and it's done. So as you see, the height of this call stack that we had will be the space complexity, right? So that would be the space complexity. And then, so how far does this go? Now, as you can see, when we're calling here, the most that it can go is the max height of the tree, actually. So this will be the space complexity. What is it? Well, it's technically log of n if it's a balanced tree, because assuming there's n number of nodes and it's perfectly balanced, then the height of this tree, if it's balanced, it will be O log of n. But if your tree looks like this, which is not balanced, then the height is also n because it's not balanced. So there's n number of nodes, and then because it's not balanced, there's also n number of height, right? All right, so that's a good explanation of trees and traversal. Okay, cool. So a lot of the times they could ask you to do a recursion, but iteratively, because that's actually a very popular thing to ask in interviews, because they just want you to know if you can do it. So if you just looked at what I did with the call stack, you'll realize that that's kind of the same thing that you can implement, but with an actual stack, like a data structure. So how do you do that? I'm not going to go through like the same thing, but usually what you do is you use a stack so that you could remember all your values, and then you pop off the value the same way that the call stack does. So let me show you how you do that. So, okay. So first, you want a stack. All right, so first we're going to use a stack, just like a call stack that we use, but this time we're going to use an actual stack to store these values that we remember, and then we pop it off when we're done with it. All right, so kind of like the base case we just did before, but a little bit different this time. If root is not none, then we're gonna start popping. We're gonna start pushing the values in. And then we're gonna have 2 values. We're gonna have one, which is the tree node, so we could actually use it so that we can iterate through. And then we also have the depth number, which is here. What is the 1 here? Cool, right? All right, and then we'll start depth as 0. And then usually, imagine if your root is none, then we're gonna skip this part, because this part makes sure that your stack is not empty. As you can see, remember when we did the stack on the iPad? There was always something in the stack until we were done the function and it was complete. Like there was always a stack growing and shrinking until the last bit, and then once we're done, then the stack is gone. So that's why the stack we do while stack is not empty. So it'll keep doing stuff. So the current depth will be the whatever that's in the stack. So usually in the head it starts like that, and then if root is not none, and then depth will be the max of either the new depth that we have on the stack, or like a global maximum that we've had already. So like that, and then stack append. So then we got it. So depth is the thing that we're gonna output at the end. That is our answer. And then so then now stack, we're gonna be appending left and right, kind of like how we do the children's left and right. We're gonna put them left and right. Okay, we're gonna get the current depth. So the reason why we add +1 is because that's how you initialize like what depth you are at, and obviously it's +1 because you're going down once more. So we're going to do the same thing with the root of right, the right side. Okay, and then you return, this is when you're done, and then you return depth. Let's see if it works. Oopsies, current depth +1, root, appendix exactly to oopsies. Also the error there was that I didn't put parentheses between, because what I'm pushing is actually a tuple of int and also a tree node. So yeah, okay, cool. So it works. We submit it, and yeah, it works. That's pretty cool. So yeah, so that is how you do it iteratively. And the time complexity is the same thing because you're visiting all the nodes at most once. And then also in terms of your stack, the size that it gets as most is O of log n if it's a balanced tree, and if it's not, it's O of n. Cool. So yeah, that's pretty much it. It's an easy problem, but it's a good fundamental to practice on to convert recursion to iterative. So all right, see you in the next one.